Welcome to my talk. I'm Takashi from NTT. I will talk about our work on the impossibility of post-quantum zero knowledge in constant rounds. This is a joint work with Nai-Hui Chia, Chung, and Qipeng. First, let me recall what are zero knowledge proofs. Zero knowledge proofs are interactive protocols between two parties called the prover and the verifier, where the prover tries to convince the verifier that a given statement X belongs to some language L. We require zero knowledge proofs to satisfy the following three properties. The first is completeness, which means that if the statement is true and both parties run honestly, then the verifier accepts with probability 1 minus negligible. The second is soundness, which means that if the statement is false, then the verifier accepts with negligible probability. And the third is the zero knowledge property, which roughly means that the verifier learns nothing beyond the fact that the statement is true. In the next slide, I will explain a little more detail about the definition of zero knowledge. Formally, zero knowledge is defined as follows. For any verifier V, there exists a simulator S. For any distinguisher D, D cannot distinguish the two words, real world and ideal world. In the real world, verifier is given some auxiliary information, AUX, interact with the honest prover P, and finally output some output out. On the other hand, in the ideal world, the simulator is given auxiliary input AUX, and it is not allowed to interact with the prover at all and simulates the output out. And we require that these two words are indistinguishable for D, and this captures the intuition that verifier does not learn anything from the interaction between P. And in the traditional notion of zero knowledge, we require classical zero knowledge where everything including V, S, D, and AUX are classical. On the other hand, when we consider security against quantum adversary, we have to think about quantum zero knowledge where everything is replaced with quantum algorithms or quantum states. And also, usually a simulator is assumed to be a polynomial time machine, but sometimes we allow simulator to be expected polynomial time. And next, I will explain what is called black box zero knowledge. This is a special class of zero knowledge where the simulator depends on the verifier only in a black box manner. In the general zero knowledge, the simulator is allowed to depend on V in an arbitrary way, so black box zero knowledge is a stronger requirement than the general zero knowledge. And there were several reasons why we study black box zero knowledge. First, the black box zero knowledge captures simulation of most known zero knowledge protocols, and there are very few non-black box simulation techniques. Moreover, those protocols with non-black box simulation often rely on very artificial constructions, and their efficiency is far from practical. Therefore, black box zero knowledge captures a wide class of natural constructions of zero knowledge protocols, and so it is interesting to study the limitations of black box zero knowledge. Especially in this work, we focus on post-quantum zero knowledge protocols, which are classical protocols that satisfy quantum zero knowledge, that is, secure against quantum malicious verifiers. One may think that we can obtain post-quantum zero knowledge protocols by just plugging quantumly secure assumptions into non-classical zero knowledge protocols. Unfortunately, this doesn't work in general, because we often rely on a technique called rewinding in proofs of classical zero knowledge. Roughly speaking, rewinding is a technique to run the adversary many times to get useful information for simulation. But a quantum algorithm may perform measurements that are irreversible, and so we cannot rewind quantum algorithm in general. For this reason, it is often much more difficult to prove quantum zero knowledge than proving classical zero knowledge, even for the same protocol. Here I review what are known about classical and post-quantum zero knowledge protocols. The first zero knowledge proof for NP was given by Gorahi, Mikali, and Wigderson in 1986. In their protocol, polynomially many rounds are needed for achieving negligible soundness error. After that, there have been many works focusing on reducing the round complexity, and constant round protocols are known in 90s. However, those works only consider classical zero knowledge, and it was unclear if these protocols satisfy quantum zero knowledge, even if we assume that all building blocks are secure against quantum adversaries. In 2005, Watrous showed that GMW protocol satisfies quantum zero knowledge if we rely on quantumly secure Raman functions. However, the protocol needs polynomially many rounds, and moreover, Watrous technique cannot be directly used to prove quantum zero knowledge of these classical constant round constructions. So it had been open to construct constant round post-quantum zero knowledge. Recently, Bitansky and Shimeli solved this open problem. However, their security proof relies on novel non-black box simulation technique, and so there still remains the following question: their constant round post-quantum black box zero knowledge protocol? In this work, we give a negative answer to the question. We prove that there does not exist a constant round post-quantum black box zero knowledge arguments for NP, even with quantum expected polynomial time simulation, unless NP is contained in BQP. Because it is believed that NP is not contained in BQP, this is a strong negative evidence about constant round post-quantum black box zero knowledge. In particular, this demonstrates an essential difference between classical and post-quantum black box zero knowledge, because constant round classical black box zero knowledge is known to be possible, as I already mentioned. Also, this theorem justifies the usage of non-black box simulation in the work by Bitansky and Shimeli for achieving post-quantum zero knowledge in constant rounds. From now, I will give a technical overview of the proof of our impossibility result. Our starting point is the impossibility result by Barak and Rinder in the classical setting. They show that there does not exist constant round classical black box zero knowledge with strict polynomial time simulation for NP unless NP is contained in BPP. Here, strict polynomial time simulation means that the simulator always runs in some fixed polynomial time rather than expectation. For proving this theorem, they show the following lemma. In the lemma, we consider a verifier that continues running with probability epsilon equal 1 over poly in each round and otherwise abort. And I remark that this V works honestly whenever it does not abort. Then the lemma says that the simulator must query V at least poly of epsilon inverse times. And then our observation is the following. This lemma means that the simulator must learn epsilon because it has to decide how many queries it makes depending on the epsilon. Then, if distinguisher D can detect that the simulator learned epsilon, then it can distinguish simulation from the real world and can break the zero knowledge property. And next I will explain how to complete our proof based on this idea. So our proof can be divided into two steps. In the first step, we prove a quantum version of Barak-Linder lemma. That is, we consider the epsilon non-aborting verifier, and then we show that the simulator must query V at least poly of epsilon inverse times to let V accept, unless NP is contained in BQP. And I will not explain the details of how to prove this lemma, but we rely on the observation that the proof of the original Barak-Lindell lemma in the classical setting is related to Fiat-Shamir transform, and so we can rely on techniques developed in the context of Fiat-Shamir transform in the quantum random model to prove the quantum version of Barak-Lindell lemma. In the next step, we consider a verifier V tilde, which is given or auxiliary input initialized to be the uniform superposition of 0 and 1, and when all equal 0, then it just runs the honest verifier, and when all equal 1, then it runs the epsilon non-aborting verifier for sufficiently small epsilon, depending on the expected number of queries. And I remark that because its auxiliary input is actually superposition of 0 and 1, so it runs these two cases coherently. And suppose that V tilde accepts in either a real world or simulation. And in the real world, the auxiliary qubit should collapse to state proportional to 0 plus epsilon to the k1, where k is the number of rounds, because when augs equals 0, then it just runs the honest verifier, which always accepts. And on the other hand, when augs equal 1, it runs epsilon non-aborting verifier, which accepts without aborting, with probability epsilon to the k. On the other hand, in the simulation, the auxiliary qubit should collapse to almost 0 unless the number of queries is too large by using the quantized version of Barak-Lindell lemma. And here I remark that epsilon is 1 over poly and k is a constant because that is the number of rounds, and we are considering constant round constructions. So epsilon to the k is also 1 over poly, and so the difference between these states can be noticed by swap test. This means that distinguisher can distinguish the real world and simulation, which means that it breaks the zero knowledge. And this completes the proof of impossibility of the zero knowledge. As additional results, we also show some impossibility results about what is called epsilon zero knowledge. The epsilon zero knowledge is a slightly relaxed version of zero knowledge, and please refer to our paper for the definition of epsilon zero knowledge. In our previous work, we constructed a 5-round post-quantum black box epsilon zero knowledge for NP, and on the other hand, in this work, we show that 3-round or constant round public coin post-quantum black box epsilon zero knowledge for NP is impossible unless NP is contained in BQP, and there was a gap between the upper and lower bounds, but this gap was closed by subsequent work by Lombardi, Ma, and Spooner, who gave a 4-round construction. And actually, they showed something stronger than epsilon zero knowledge, as I will explain next. Actually, so LMS21 constructed constant round post-quantum black box zero knowledge for NP with quantum expected polynomial time simulation. At first glance, this seems to contradict our main impossibility result. However, there is actually no contradiction, and this situation comes from the difference of computational models. In our work, we consider quantum Turing machines with measured runtime, which performs a measurement to check if it holds in each step. On the other hand, they consider a quantum Turing machine with coherent runtime, which doesn't perform such a measurement. And indeed, we implicitly use the measured runtime version without explicitly stating so because we thought that it is natural that quantum Turing machine should be able to know when it halts. However, LMS21 pointed out that this is not the only possible model, and by considering a coherent runtime version, they can overcome our impossibility result. Please refer to LMS21 for the details. Let me summarize my talk. We showed that constant round post-quantum black box zero knowledge is impossible with a major runtime expected polymer time simulator. And we also show that 3-round constant round public coin post-quantum black box epsilon zero knowledge is impossible. And this is the end of my talk. Thank you for listening.